who's talking about LevioSA, lightweight secure arithmetic computation.
Thanks, Ali, and thanks for inviting me here. I'm going to talk about some recent work on lightweight secure arithmetic computation. Since we have an implementation, we had to name it, so we called it LevioSA. This is joint work with Kermit Yuval and Antonio. So we've seen a lot of talks in the past 2 days on secure computation. We know this is feasible since the 80s, but what about efficiency? This is one of the aspects we are talking about in this workshop. Just so that I put this work in context, I want to say this talk is going to be about constant number of parties. For the most part, it's going to be 2 parties. I'll tell a little bit about multi-parties at the end. We're going to focus on functions expressed as an arithmetic circuit as opposed to a Boolean circuit. So, we're not talking about any garbling techniques in this paper, but functionalities that are expressed as an arithmetic circuit over some finite field. And one can also express integer computation in this space, but this is sort of the kind of tasks that we are looking for. And we want full security, meaning security against malicious parties up to n-1 corruption. Just one slide about motivation. A lot of things that we care about can be expressed as an arithmetic circuit. A lot of threshold cryptography, which is relevant to the blockchain space, can be expressed as an arithmetic circuit. Neural network computations can be expressed. They are basically matrix multiplications over some integer space and can be expressed as an arithmetic circuit. Pattern matching, statistics, etc. All of these fall under this category. And I was speaking with Mike and Abhi yesterday, who was also saying set intersection, which is sort of part of pattern matching, also can be expressed as an arithmetic functionality. So in general, we are all familiar with this blueprint, at least in crypto. If you want to construct a secure computation protocol, you start with something that is secure against a benign adversary that we call a passive adversary, and then we boost the security against malicious parties. Now, what is this talk about? This talk is primarily about understanding what does it take to do the step 2. What is the overhead of getting active security from a passive secure protocol? Okay. Just before we get into the main results, I want to say sort of in this space, the main building blocks that people have considered when you talk about secure computation is, of course, oblivious transfer. This is extensively used in Boolean computations. It's complete for secure computation. We know what this functionality is. There are many, many efficient implementations. We just saw the previous talk, which supposedly is going to do something better than what we know with OT extensions. And this has also led to like all the recent improvements in fast Boolean secure computation. I want to talk about a slight extension of oblivious transfer, which will also be relevant in this work, which is sort of K out of N OT, where the receiver can get an arbitrary K subset from N entries of the sender. A second primitive that's used here, more relevant to the arithmetic space, is the oblivious linear evaluation. Again, you've all defined this. I'm not going to get into what this functionality is about, but this is a second building block that's used in and more focused on secure arithmetic computations. So what do we know in this space? I'm talking, again, it's sort of a biased presentation, but I sort of want to list some generic techniques in the space of getting secure arithmetic computation. If you wanted 2-party computation, say in the OLE hybrid, meaning assuming that there is, you're using some OLE protocol in a black box fashion, there's been a series of works, and I'm talking about the ones that we're going to look at more things that were concretely efficient, and the work of Dotling et al. From CCS 2017 shows that you can get this, where you can get a secure 2-party arithmetic computation where for every multiplication gate in your circuit, you have to invoke a malicious OLE protocol 22 times. And of course, there are works that, cast an arithmetic function, like you can implement OLE in the OT hybrid and then use it in the arithmetic functionality. In this case, again, starting from the work of Gilboa in 99, now you can show that you can construct a malicious protocol here where, again, every multiplication gate is going to invoke the OT functionality 6 log f times, where log f is sort of the size of the field elements. And then there has been more recent work which uses like tailor-made oblivious linear OLE implementations based on like LWE-based OLE implementations here to get malicious security. Why I say tailor-made is like you fine-tune zero-knowledge proofs to get malicious security. So this is sort of, in general, the state of affairs. I should say that, again, I made these slides like 3 months back. There's been more work in sort of improving this, at least in this last category where you have more efficient zero-knowledge proofs for constructing malicious protocols. The main question that we are trying to address here is, what is the overhead of achieving active security given black box access to any passive OLE? Not any tailor-made, not specific implementations, assumptions, so forth. Given any passive OLE implementation, what is the cost of getting active security? So the main result that we have is that we show a compilation where we use constant black box invocations of a passive OLE. Given that this is, I keep talking concrete efficiency, I should tell that if your circuit is nice enough, and by nice I mean if they are wide, sufficiently wide, then this overhead is actually 2. Now, for people who are familiar with like passive protocols in the space, you should just think of this as GMW. It's the passive version, and we get it twice at the cost twice of GMW. And this is the communication overhead that I'm talking about. The computational overhead, I'll tell you a little bit. This is also not that much higher. You can think of Yao also? No, but this is, yeah. So Yao, I mean, I can talk about Boolean later. There has been work, but this is primarily for arithmetic functions. So just another, like if you instantiate, if you cared about just getting active OLEs, if you think about just pre-processing some random OLEs and then using it the way Yuval mentioned as offline and online, if you just wanted to get active OLE from passive OLE, we show that you can do it at the rate of 2 black box invocations of the passive OLE protocol. And just to sort of bring up the previous work, Dotling et al. Show for the black box case, they need 22 invocations of a malicious OLE. And the work of Ghosh et al. Show, again, with a tailor-made OLE, they actually show you can do 2. So it's not quite black box in any implementation, but they get this number 2 for a very specific passive OLE. And it also requires... Yes, so Yuval is right. The 22 refers for any generic OLE, but here, I mean, the 2 is not quite, I mean, it's hard to put it in context. It's 2 invocations of this very specific passive OLE protocol. All right, so again, I'm going to talk about, this might sound cryptic a little bit. If I have a few minutes at the end, I'm going to show you we can construct an active OLE that is better than a passive OLE. All right, so some techniques. So the main technique that we follow here is, yes?
This is a theory itself, or is this like, you think this is the best way of doing MPC? I don't care about live talk, blah, blah, blah,
I would never say best, because then most of us can go home. But I think this gives sort of a generic approach of thinking about when you want to construct actively secure protocols, think of passive, see the best protocol, try to amplify it to active, and this is the space where at least Yuval, Karmeet, and I in the last couple of years, we focused on improving this overhead. And being generic in the passive protocols helps you generalize to many settings.
So I know there are many dimensions, but you think there's at least
competitive, like in.
I'll give you performance. There is an implementation, so I can give you some performance at the end.
Again, for clarification, when you talk about active versus passive OLE, you're talking about the initial business cards exchange phase, right? That's where it comes to
So
play.
I mean, it has applications to the initial business. Like in Yuval's thing, the offline pre-processing phase requires a malicious protocol for which you can use our techniques. But in general, we are talking about, take GMW. You just need OLEs to do arithmetic functionality. If you want to get malicious security, we show that we can get GMW like twice the cost based on passive OLE. I don't know if I'm making sense.
We don't have very good PCBs for OLE correlations. We get, say, very good OP generation, but we don't have a very practical way of generating OLE using traditional passive OLE without this business card.
I see. Okay.
So, and I also might assume that in some regimes, even the computational efficiency of this could be better than using PCGs. Yeah, at least currently. So on a high level, I mean, this work, if I had to sort of trivialize the work, it is about using the IPS approach, which is one of the beautiful works that actually introduced this kind of, compiling passive or, milder components to, by boosting security. What we have done is sort of tighten various aspects of this compiler to get an efficient protocol. Okay, and on a high level, I'll try to explain IPS. It's hard to explain in 3 slides, but whatever I can, I'll try to do it in the next 3 slides. On a high level, this approach by Ishai Prabhakaran and Sahai is to take 2 kinds of MPC protocols and combine them to get something of better security. The two milder building blocks that we are going to use, one is active multi-party computation with honest majority. This is something that we know since the 80s, BGW, CCD, like we've seen all these works that show how to get active MPC with honest majority. And this is, as Yuval said, you don't need any cryptography, it's non-cryptographic. And the second one is a passive protocol against dishonest majority. So combining these 2 protocols, we're going to get active security against dishonest majority. And this is the IPS approach. So let me just quickly give a pictorial. What do I mean by active MPC with honest majority? We're going to have this sort of client-server model where you imagine that we have 2 clients that have inputs. There are a set of servers. The clients are going to distribute their inputs to the servers. The servers will do the computation and return the answers to the clients. In this model, we are going to assume that an adversary can corrupt at most one of the clients and at most half of the servers. So we are trying to construct protocols in this regime. All our classic honest majority protocols fits in this model. Okay, so this is the first component. The second component is passive 2-party computation against dishonest majority. Here, the model is that an adversary can passively corrupt at most one of the 2 clients. Okay, and here, as I said, for people who know this space, GMW is the classic protocol, and we are going to use the GMW protocol for instantiating this. And GMW protocol for evaluating secure arithmetic functionalities essentially proceeds as, you secret share your inputs, and then you invoke a passive OLE for every multiplication gate. This is how the GMW protocol proceeds. So we're going to take the IPS approach says you can take these 2 components, combine it to get malicious security against a dishonest majority, or in this case, against 1 client. So before I go into showing this compiler, I just want to say we need one ingredient which we all know, which is Shamir secret sharing, which allows you, using a polynomial, to store your secret at P of 0 and then be able to distribute your secret across n servers where up to T of them cannot learn anything, and beyond that they can recover the secret. We're going to do a slight extension of the Shamir sharing, which is referred to as pack secret sharing, introduced by Franklin and Young, which says, well, why store only one secret at P of 0 in the polynomial? You can store more. This affects the parameter of the threshold parameters of privacy and reconstruction, but this is sort of going to give us this amortized benefit that normal secret sharing will not give us. Okay, so just two key properties that, to understand the IPS compiler, the two key properties of the secret sharing is that knowing up to t values does not compromise privacy, and changing up to the error correction threshold, if you think of this as error correcting code, will not affect correctness of the computation. So what is the IPS approach? Again, this is just a one slide version of IPS approach. It says that you're going to use the honest majority protocol to implement whatever functionality you care about. But in the real world, there aren't these servers that do the computation. Instead, you're going to have these servers emulated by the two parties themselves. The state of every server is going to be in an additively shared form between the clients, and the clients are going to emulate each of these servers. Okay? So in essence, we are emulating the outer protocol, except that you don't have the servers. You're going to use what the passive or the inner protocol to emulate these servers. Now, the outer protocol gives you security only if there is an honest majority. To ensure that we get this property, we need to make sure that even if when these servers are emulated using a passive protocol, you somehow can enforce honest behavior on a majority of these servers. And the way you're going to do it is that each client monitors the other client on up to, let's say, T of these servers, meaning how they perform in these actions. I know complete state of the server, and I will check the other person's behavior on T servers. Now, this, by a classic cut and choose analysis, you can show that, well, if the adversary tries to cheat in many servers, the adversary will be caught. But if the adversary cheats in very few, the error correction of Shamir sharing kicks in to get correctness. Roughly speaking, again, I'm trivializing a lot of things, but this is how the IPS approach essentially works. Okay? So, in the interest of time, I'm going to skip one more ingredient that we had from a previous paper. I'll talk about it maybe in one sentence in another slide. So this is, as I said, what we do is we take the IPS approach and we construct, we sort of tighten the parameters and show how to get all this efficiency that I talked about. Let me just sort of give you a pictorial diagram of how we would get an active OLE from a passive OLE. Rather than talk about the general secure arithmetic computation, which does follow from the IPS approach, let me just take you this instantiation of getting active OLE from passive OLE. Okay, so imagine that we want to do many OLEs, and again, the overhead that I claim of 2 comes when you want to do this in a batch setting. When I want to do many OLEs at a time, then I'm going to get this 2 overhead. So what do? So let's say that you have M inputs, so they have AI, BI, the sender has AI, BI, and the receiver has XI. Now, I'm just going to give you the outer protocol, but you push it through the IPS compiler, you're going to get the efficiency. So how does the outer protocol look? Well, each Alice and Bob are going to encode their inputs using pack secret sharing to get the code A1 through AN, or the set of shares A1 through AN, B1 through BN, and X1 through XN. They're going to give AI, BI, XI to the server. The server is going to, each server is going to locally just compute an OLE computation. So they're going to take AI, XI, BI and compute AI, XI plus BI. And then there needs to be one check. Remember, we need this to be actively secure. Now, it's not clear when the clients share their inputs, are these sharings, are they correct? And for here, we need to do a small test to check that all the shares are good. To do this, this is where we sort of tighten the analysis. We introduce a new kind of test that, well, new kind of analysis, not new kind of test, which says that if I want to check a set of shares, if they are all valid Shamir shares, think of it as getting verifiable secret sharing in a different way. Now, you can imagine that these servers get access to some randomness, let's say through some coin tossing protocol, and they are going to share amongst themselves a random linear combination of these shares and check if the random linear combination is a valid set of shares. Okay? And this is what the slides that I skipped show, that we have an improved analysis of the soundness of this test. When we have many, many vectors that we want to all check if they are valid Shamir shares, we do this random linear combination to check it, but we give an improved soundness analysis of how many servers have to be watched and so forth. We give a better soundness analysis in this space. Not in this work, actually in a previous work, again joint with Kermit and Yuval. So after this is done, if the random linear combination test passes through, then the servers are going to pass the CIs, and from the CIs, Bob is going to decode and get the output. This is essentially our protocol. This is the outer protocol. You can ask what is the overhead of doing the IPS approach. It's just about setting up watch lists, which is running a k out of n oblivious transfer. So besides this, this is essentially our approach. Ensure, to do every multiplication AI xi plus bi, when you emulate it using an inner protocol, will invoke one passive OLE. This is how you should think of it. So the cost of this whole protocol, the number of OLEs, the number of passive OLEs to emulate this protocol, is the number of servers that you need to do. So in essence, if I want to do m OLEs, I'm going to encode it to n servers, and I'm going to do this. Roughly what we care about is this ratio n divided by m. And this we show for our soundness analysis. This, as I'll give you a table. We show that for m large enough, like close to 500,000, this becomes 2. But even for smaller values, it's not too high. Okay, so just to, I want to stress here that the key feature in this whole thing is that we can base our protocol like black box on any passive OLE. And the main features are that it's more flexible. You can use any, you don't need tailor-made, you don't need LWE based or any of these things. You can use any OLE for instantiating the passive protocol. You could even imagine maybe physical implementations of a passive OLE protocol. In particular, compared to previous work, you don't need this sort of zero knowledge friendliness to get active security. You can use any off-the-shelf software or hardware implementation. A second feature that I want to talk about is that we can even go weaker than passive OLE. You can even imagine your OLE has some correctness error, like for HSS-based constructions that Yuval mentioned in the previous talk, as well as if you, even in some OLE implementations, the privacy can be compromised with a small probability. This happens when you use LWE-based OLE implementation, when you set the parameters more aggressively. So in one slide, I sort of want to tell you this thing where I mentioned that you can get active better than passive. The extension is with respect to these things where if you use a leaky OLE, and by a leaky OLE, I mean one that compromises privacy with some small probability. So if you use LWE-based OLE, where you implement a simple additively homomorphic encryption using LWE, you can imagine that if you set the parameters aggressively, it can happen that the receiver learns some small fraction of what A and B could be. There's a small leakage on the values A and B to the receiver. Now, I want to say that you can put a leaky OLE in the IPS compiler and still get some benefits from the IPS approach. But the one thing that, so let me just sort of show you here. This is the diagram we had. And what happens if you use a leaky OLE to implement each of these servers' multiplication? In essence, what happens is that the adversary, let's say the receiver here, learns T full views of the servers. This is just because of the watch list. But in the rest of the servers, it could, whatever my OLE leaks, it's going to leak. So it could leak some small amount of information in the rest of the servers. So we show how to get to accommodate a leaky OLE. It turns out that if we use a leakage resilient secret sharing scheme, you can get it. So the same IPS compiler works as long as I can show that this small leakage on the remaining servers does not affect, security in any way. And leakage resilience, there have been several works. There have been also several works on even leakage resilient secret sharing. The work that, given my time limit, I just want to sort of talk about the one work that's closely relevant to what we did, which is the work of Benamuda et al. From Crypto 2018, where they actually analyze the leakage resilience of in the way we want it, which they call local leakage resilience, for both additive secret sharing schemes and linear secret sharing schemes like the Shamir secret sharing scheme. So they kind of show that when you consider things mod p for some prime p, additive sharing has some good features, but Shamir sharing, they are able to show some small kind of benefit in terms of leakage. You can leak up to log p bits per share, and you can tolerate t equals n minus square root of n. Now, I should say that this is not useful yet for the IPS compiler, because you are going to need honest majority. T needs to be less than n by 2. And I sort of want to point out here, this T here refers to the degree of the Shamir sharing scheme, not the watch list size. There could be a confusion here. Let's ignore the watch list size for now. This T refers to, the degree of the code. And this is not yet enough for our setting where we want to invoke this leakage resilience when T is less than n by 2. So actually, I should also say there's been more works. Again, I'm not listing all the works here. There has been, at least in the last, I think, 2 months, I saw 3 papers on ePrint that talk about leakage resilience of secret sharing, but none of them are relevant to our setting, mostly because it's not in this regime. But I should point out that there is something nice about our setting, in that we don't need to, all these previous works that talk about leakage resilience care about leaking more than 1 bit of information on all these shares. But in our setting, when we think of LWE and the kind of error that comes from LWE, you can even think of leakage which is less than a bit in the sub-bit regime. And this was not sort of analyzed in the previous works. And one of the things that we do here is we give a new leakage lemma for the sub-bit regime. And I should say that we don't have a full proof in that, just taking from, the LW, that proves it for the LWE setting. Let me just put the context. Our leakage lemma refers to a very specific kind of leakage, which hopefully we are trying to extend it to the LWE kind of leakage. Our model is this exclusion set model, where the adversary gets to pick a small set for each of the servers, or for each of the shares, and it gets leakage whether it belongs to the set or not. Okay? And when I say small, because this can be fine-tuned based on how aggressive you set the parameters. The size of this exclusion set is determined by that factor. Anyways, long story short, for this regime, you can prove some meaningful parameters where we can get active security starting from a leaky OLE. And the current techniques that take LWE to do these things actually give worse passive OLE than what we get through active OLE. And it's only in this sense that I mean that our active OLE is better than passive OLE. And how much time do I have? I'm out of time. Okay, I had some implementation slides which you can come and ask me offline. This is a table which says the n by m values that we get for different values of m. We measure our performance compared to the state of the art, Overdrive from Eurocrypt 2018. This is one of the main works, and we actually show that we compete with them in generating what are called beaver triples, but But to invoke our protocol, we don't need beaver triples. We can just use our whole IPS protocol to get, and that would be much like better than generating beaver triples and computing the functionality. So just to conclude, we get the first concretely efficient sort of general passive to active compiler. We show how to get active OLEs to from any passive OLEs. We give an implementation, and then we have some nice connection to leakage resilient secret sharing that gives us like more better like concrete efficiency. Thanks.
We have time for a quick question.
For two-party computation, how would it compare to just garbled circuit and cut and choose and sort of optimize techniques for that?
Right. So if you use, first of all, you have to convert like field arithmetic to Boolean. This is already like an overhead. But also the techniques for like passive to active. I mean, we have a work that shows you can do this with constant overhead, but that requires algebraic geometric codes and so forth. But if you didn't want to use that, the overhead is typically security parameters. So active to passive is like 40 or whatever is your thing. So you don't want to do that.
Like then for SHA in terms of communication.
Oh yeah, based on the work of Shao, I think it is 17 if I remember. No? About 10? Okay, it's about 10 now for 40-bit security.
I think we should take the rest of the questions offline. We'll start again at 10:50 for